Hello and welcome to today's lesson on resolving vectors, which is part of the forces topic in GCSE Combined Science Physics. So in today's lesson we're going to look at how you can resolve vectors into different components. So if we've been successful and learnt in today's lesson, we should be able to define a vector quantity and how we can resolve them, describe how we can represent vectors, and finally explain why we resolve vectors in the first place. So we're going to follow 6.5.4.1 resultant forces in this particular part of our lesson. So if you have two vectors which are not at 90 degrees to each other, you can still add them via scale diagrams, but to find the resultant vector you've got to use something called the parallelogram of forces. So how to draw a parallelogram of forces is as follows. In the first step you draw in the same length vector as vector 1 as shown on the diagram with the same angle to the opposite side of vector 2. You then draw in for your second step the same length vector as vector 2 with the same angle on the opposite side of vector 1. Now this has produced a parallelogram of forces. So therefore, to work out your resultant vector, you draw in a straight line from the start of the vectors to where our new lines that we've just drawn meet up. We can then find the size of the resultant vector by measuring the vector with a ruler and then converting the value with a scale. We can then find the angle of the vector by using a protractor to measure the angle of our resultant vectors. Now, as well as adding two vectors together to get a resultant vector, it's also often very useful to break a diagonal vector into its perpendicular components, its horizontal and its vertical component, as it's easy to describe the motion of an object and do any relevant calculations. So let's consider the following resultant vector F. So a single force can always be resolved into the two component forces at right angles to each other. Now, to resolve means to split our resultant force into two separate ones. So our single force can be resolved into horizontal and vertical components as shown on the following diagram. So here our resultant vector is denoted as F, but there's an angle phi from the vertical as shown on the screen and an angle theta as shown from the horizontal on the screen. Now, our resultant vector can be thought of as a sum of its vertical component Fy and its horizontal component Fx. Fy because of the y-axis and Fx again because of the x-axis. Now we know that from Pythagoras, we know that f squared is equal to fy squared plus fx squared. Now let's just show you where this comes from by swapping the position of the vertical axis so you can see that's just a right angle triangle that's been made with our horizontal and vertical component. Now remember, in this process you've got to use the angle produced by the vectors, not the direction reference, so look at the angle used carefully. Now we can actually work out our horizontal component by carrying out the equation fx is equal to f cos theta, whilst we can work out the vertical component by saying Fy is equal to f sine theta. Now we can derive these both from trigonometry ratios. So we know that sine of an angle is equal to the opposite side over the hypotenuse side, which if you look in this right angle triangle is Fy over f. So we can rearrange it to make Fy the subject by saying Fy is equal to f sine theta. So this again, like I said, comes from trigonometry ratios. Whilst cos theta is equal to the adjacent side of your triangle divided by the hypotenuse side of your triangle. So cos theta is equal to fx over f, where fx is our adjacent side to our angle and the hypotenuse is f. So we can rearrange this and make fx the subject by saying fx is equal to f cos theta, once again coming from trigonometry ratios. So these equations can be used to calculate the horizontal and vertical components. So let's say, for example, we've got a resultant vector at 10 newtons at an angle of 40 degrees. So Fy is equal to 10 sine 40, which is 6.4 newtons on your calculator, and Fx is equal to f cos theta, or 10 cos 40, which is 7.7 newtons. Now the two component forces added together give the same effect as the single force. Now remember, we don't just add the two horizontal and vertical components directly because we're not thinking of a scalar, we're thinking of a vector, so we've got to consider their direction. So let's have a look at another example. Now it doesn't have to be a force, it could be any vector we do this for. So let's say, for example, we've got a velocity with a magnitude of 6 meters per second with a direction of 60 degrees from the horizontal. So how do you work out the horizontal component? Well, it's going to be F cos angle, or 6 cos 60, so it's 3 meters per second. Let's now work out the vertical component. It's going to be F sine theta, so it's therefore going to be 6 sine 60. So we can see we've got our horizontal component and we've got our vertical component. Now, like mentioned before, the two component forces added together give the same effect as that original resultant vector, which is 6 meters per second in this case. You don't add the vectors directly because you've got to consider their direction. Now we can also resolve vectors by using scale diagram methods as well as mathematics. So if we look at the scale of our scale diagram, so let's say for example 1 centimeter equals 10 newtons, to then work out the size of the horizontal and vertical components, you would make a right angle triangle with the resultant vector as the hypotenuse. You would then measure the length of the vertical vector with a ruler and convert it to a force via a scale. You then measure the length of the horizontal vector with the ruler and convert it to a force via the scale. So what do? We produce a right angled triangle with the resultant vector as the hypotenuse. We measure the length of the vertical vector and then convert it via a scale. Then we measure the length of the horizontal vector with the ruler and convert it via a scale. Now again, remember, the two component forces added together give the same effect as the overall singular vector. Now remember, they don't add directly to form the resultant because you've also got to consider their direction. So why is this example important in the real world? Well, we've got to resolve a resultant vector into its horizontal and vertical components to help with the principle of projectiles, which is the fact that horizontal and vertical vectors such as force or velocity are independent of each other. This means that horizontal and vertical vectors do not affect each other, which is a reason why all objects fall at the same rate vertically, irrespective of their horizontal motion, because objects experience the same vertical force, gravity. So this means, for example, a ball thrown sideways hits the ground at the same time as a ball dropped. This means a parcel dropped from a moving car and a parcel dropped from a stationary car hit the ground at the same time. This means an object thrown from a moving train hits the ground as an object thrown by a person standing still. Because if we think about it, all objects are pulled to the ground via the force of gravity, so all objects have the same downward acceleration. Now any horizontally moving objects experiences the same downward acceleration as the other objects, because horizontal vectors do not affect vertical vectors and vertical vectors do not affect horizontal vectors. So to clarify this idea, vectors at right angles to each other do not affect the size of each other. Horizontal vectors will only affect horizontal motion, vertical vectors will only affect vertical motion. So this tells us that only the vertical vectors acting on this object will affect its vertical motion, and the horizontal vectors will not affect this at all, and vice versa. So this is why we've got to resolve a resultant vector into horizontal and vertical components to allow you to work out the horizontal and vertical motion on an object. So let's just summarize what we've learned in today's lesson. Scalar quantities have a magnitude only. Vector quantities have a magnitude and an associated direction. A vector quantity may be represented by an arrow. The length of the arrow represents the magnitude, and the direction of the arrow the direction of the vector quantity. A number of forces acting on an object may be replaced by a single force that has the same effect as all the original forces acting together. This single force is called the resultant force, and you should be able to draw vector diagrams to illustrate the resolution of forces, equilibrium situations, and the determination of the resultant of two forces to include both magnitude and direction. So if we've been successful and learnt in today's lesson, we should be able to define a vector quantity and how we can resolve them, describe how we represent vectors, and finally explain why we resolve vectors. So I hope you've enjoyed today's lesson on resolving vectors, which is part of the forces topic in GCSE Combined Science Physics. Thank you very much for watching today's lesson, and as always, have a lovely day.